this video will finish off the last of the one-star questions. So let's get started. We finished off with 27 last time. The next one-star question is question 31. Alright, so question 31 has a reference to figure 17.28 off to the side there, saying it shows a satellite dish used for receiving TV signals. You may have seen this on your own home or homes nearby you. I know I have one on my roof for receiving just free-to-air TV, as my house is in a bad reception point, but you may have seen them around. Have a look at the roofs of the houses as you go to school next time. So the first thing's asking you, what shape should the dish be? So we've either got concave or convex. Well, do we want to focus the light hitting it, the radio waves, and remember radio waves are a type of light, or do we want to spread it out? Well, we want to focus it, otherwise we're going to get a really weak signal. So the first bit is, well, we need concave because we want to focus it. Now, answering questions like this is a good habit. So not only are we telling what our answer is, but we're giving a reason for it, and that way we can show what our understanding is. Okay, question B. Where should the signal detector or the aerial be situated, and why? Okay, well, if we have a look at that image, we can see that it is somewhere in the middle, but it is actually held out in front of it. Well, if we think about a radio waves or light waves hitting a concave mirror, they will come in parallel because they're further than a couple of meters away, and they will bounce back and hit at the focal point. Well, if we want the maximum strength, we should have it at the focal point. So focal point, again, because the waves will converge. Alright, part C. What features of the dish should be changed to improve its performance? So if we're dealing with just a simple spherical concave mirror or concave reflective surface, it's not a mirror for light, but it is a mirror for radio waves, then we should establish that, well, a parabola is going to be better than a concave mirror. So let's say that the shape should be parabolic. Why should it be parabolic? Well, remember, it removes the focus aberration. Okay, so it's removing that issue where not all the points are being focused onto one point. Okay, 32. Now, 32 asks you to prepare a table. So I have done that on Excel on my computer, and I will put down things that seem relevant here. So what I've done here is a table using a focus of 20, and then I've used a set of distance to the objects. So the questions asked us to use a concave mirror, so that means a positive focal, position of object from outside the center of curvature to inside the focus, telling us the size of the image, the position of the image, the nature of the image, and whether it is upright or inverted. So position is asking about the distance, the size is asking, well, how big is this object? So we can think about the magnification for that, really, and that'll tell us the size. We could make up a size, but let's just go with the magnification. The nature, is it real or virtual? And whether it's upright or inverted. So what I've done here is a set of distances. So I've got 5, 10, 15. Now these three are all within the focal point. Now I've chosen 10 because it's exactly half. Halves of numbers seem to be important in these sort of equations, and 5 and 15 are just spacing it out. I've also done 20 because it's the same as the focal point, so something interesting will happen there. 30, 40. Now 40 is twice the focal point, the center of curvature, and 30 is halfway between, so it shows us what's happening between 20 to 40. We could do maybe 25 and 35 in there as well, but let's not do too much. 50, 60, and I've also done 10,000. Now I've done this on Excel, so the computer does all the calculations for me. If we were doing this by hand, I would definitely recommend this one, and probably these two would be better. Yeah, the 10 one might do something interesting, but we want to save time. 40 would be necessary, so would 50, and so would 30. These other ones are more just to sort of show what's happening. Now I've chosen 2 for each range. This isn't really 2, but it's close enough, just because 2 shows us a pattern, 1 is just a data point, so 2 at least starting to show what's happening within that area. Alright, so my distance to the image, for 5 it comes up as negative 6.67. For 10 it's negative 20, for 15 it's negative 60. So we see as we get closer to the focal point, it gets further away on the other side of the mirror. Alright, now for 20 it's a division by 0. Okay, if you put a object directly at the focal point, there will be no image. Okay, let's go to 30 now. So 30 gives me 60, so it's come back from the other side. Okay, it's far away, but it's on the positive side now. 40 also gives me 40, so at the twice the focal point, we get exactly the same position. So if we put it at 40, we get it back at 40. 50 gives me 33.3. 60 gives me 30, and we see that even though these are going up by 10s, these are not going down by 10s. Sorry, 30, not 300. 10,000 though gives me 20.04, and even if I take it to as many 9s as I can put into Excel, it doesn't get below 20, so that it'll never get back in front of the focal point again. Alright, let's do our magnification. So our magnification here is 1.3, 2, 4. Because there's no image, there's no magnification. Then minus 2, minus 1, negative 0.67, and negative 0.5, negative 0.02. So the further away it's going, the smaller it's getting. Now these ones here, if we were to start classifying these, we can see these are all upright because they're positive magnifications, while these are all inverted because they are negative magnifications. We want to think if something is virtual or real. Now virtual objects are either behind the mirror, like all convex images, or in this case these 3, or they are going to be in front of the focal. Now these ones are not in front of the focal. We can't get them in front of the focal here, so let's go. These ones will be virtual. I know my V's and my U's look kind of similar, so do be careful with that. These ones here, because they are in front of the focal point, are all going to be real. Okay, so we can see then if our object is in front of the focal point, we get an upright virtual image, and if looking at the magnification, it also gets enlarged. These two here are also enlarged, but these, well, this one here isn't enlarged, it's the same size. These 3 here are all reduced, smaller. Okay, so let's do some statements here to help summarize our table here, because we've got a lot of information, but it's not really helping too much. So if we think about the distances first, we can see if it's in front of the focal point, it gives it behind the mirror. If it's at the focal point, there's no image. If it's past the focal point, and it doesn't matter where, so even the the radius of curvature doesn't affect it, we get that it's just getting closer to the focal point in general, but it is not going to be past the focal point. So we could write that as a statement. In front of F, image behind mirror, past F, approaches. Oops, that's not how we spell approaches. Approaches F from far away. So if I'd done like 20.1, for example, we'd get a very large number here. Let's do another statement. So let's think about our upright versus inverted. So we can see that if it's in front of focal, we get it upright. If it's past focal, it's inverted. We could certainly write a statement if at focal there's no image, but we can leave that till the end. In front of focal equals, oops, not inverted, equals upright. Past focal equals inverted. Okay, let's move on to our real versus virtual. So in front of the focal, we see that they're virtual, no image at the focal, and then past the focal, they're all real. So we can sort of attach that to that. In front of focal equals upright and virtual. And past focal equals inverted and real. Now, the enlargement, though, is the one place where it doesn't follow the same pattern. Yeah, all the ones in front of the focal point are enlarged, but objects that are between the focal and the radius will also be enlarged. So we could say from in front of the focal to, not including, but to the radius of curvature. So in front of focal, well, let's do it like this. In front of radius of curvature equals enlarged, past equals smaller, at R equals same, and finally no image if DO equals F. So that sort of question, while it's only at 1 star because it's not particularly hard to get this, does show a lot of really good opportunities for IP skills where you're interpreting a data table that you might create yourself in order to show general patterns. So that's a really good type of question there. Alright, so that was question 32. Did I label that? Yes. So let's go on to 33. Alright, if you're sitting at the breakfast table and a piece of dust flew into your eye, explain how you could use a spoon to observe a larger image of your eye to help remove the dust particles. So what we just did there will help for this. So if we have a look at this, we see that if we get our object, in this case our eye, close to the focal point but just in front, we see the most amount of magnification. Okay, and we create a virtual image behind it. We could also do it with a convex mirror, so the other side, but remember you have to be really close, otherwise it will flip it upside down. So let's use that. If DO is close to F and less than F, now I'm using mathematical shorthand here, you might want to use full sentences, then M will be much greater than 1. Okay, therefore the image is upright and magnified. Okay, let's move on to question 34. I do apologise, my handwriting seems to be a bit off tonight. 34, and okay, so some solar hot water systems use curved enclosures supports to hold the black PVC pipe in which water flows. Discuss the purpose of these shiny curved enclosures and the positioning of the black PVC pipe. Alright, so there's a diagram there on 17.29. We can see that there's a curve shape, and we can see that there is a black piece of pipe, not on the bottom, but slightly off a bit. So what is this shiny bracket doing? Okay, so think about it. If light hits it, it's going to be reflected, isn't it? And if it's curved into some sort of concave shape, then that reflection is going to hit it at the focal point. So then if we want the most amount of light to hit our black PVC pipe to heat it up, then we can see then that we really want the most amount of light possible to hit it, so we get the most amount of heating out of it. There's quite a lot of energy in sunlight, but a lot of it is wasted because we just don't capture it very effectively. So this is one technique to improve our capture efficiency. So we could say that the shape is to focus the light. Shininess is to reflect the most amount. The pipe is positioned at the focus. Remember that all light, parallel light, and the sun is parallel effectively for these sort of objects, especially because remember, anything further than a couple of meters away for anything regular sized, the light is effectively parallel when it hits you. The sun, while it is huge, is very, very far away, so its light is effectively parallel for us. The pipe is positioned at the focus to receive maximum light. Alright, last one star question from what I can see. Let me double check, 35. Yep, alright, so 35, figure 17.3, which is on the next page from the look of it. Yep, there it is. Shows an object with several rays reflecting from a convex mirror. Which of the rays are correctly drawn? Alright. Now we've only really covered two of the rays, so let's try to identify those two first. So our first ray, remember, is parallel from the head of the object. After it hits the mirror, it then has to go through the focus point. Now, in this case, remember it's a convex mirror, so the reflected ray will go away from the convex point, from the focus point, and we would draw a dashed line down to that focal. So looking at that, that would look something like, so here's our primary axis, mirror, object. So first line should be something like this, which means the reflected ray bounces that. Now on that diagram that we see there, we can see that's A. So line A is definitely right. Okay. So our second ray there is going to go from the head of the object straight to the focal point, okay? And then when it hits the mirror, it goes back parallel. So it's going to go something along there. So there. Okay, now this is where it reflects, and we would backtrace the second mirror. Okay, and if we have a look at that, we can see that B is that wave. So take a look at the picture, try to make sure you can see that B is that second wave. Okay, now we've got C and D. So if we look at what's happening with C there, it looks to be that, oh, there's also E, but C looks like it's bouncing after it hits this line, the same starter as B. Once it hits here, it just goes off that way. And remember, if that line is going directly to the focal point, doesn't matter where it hits, it will come back parallel. E is coming from here down there, and that doesn't make any sense at all, so ignore that. Alright, our last one is D. So D is not a type of ray that we've seen before. Now remember I said that there are two that we can use, but I've sort of just said, okay, we only need to use two. There could be three, but we can ignore that one. So the third ray goes from the head of the object to the principal axis. It doesn't go through the focal point, it goes to the principal axis. And then it bounces back at the same angle. And we can see that D actually does that. So if we think about it, yeah, it's going to hit here. I don't know what my phone, there we go. I don't know what my pen was just doing then. So it's going to go from here, straight down, and then once it hits that, go back at the same angle. Remember, angle of incidence equals angle of reflection, and because it's hitting right in the center, it's essentially just hitting on a flat surface, like it was hitting a plane mirror. If that doesn't make sense, do ask questions. So the back trace from here is this, and we can see it basically, again, all hits in the same point. So the third ray does make your drawings a little bit more accurate, but don't stress about that. 2 rays is certainly fine for me. So that means that A, B, and D are all correct rays. So there are 3 correct rays. A and B are the 2 that we're focusing on in class. D is also a true one, but you shouldn't need to draw that for anything. Maybe some of the 3-star questions, I haven't looked at them yet, but A and B will certainly be sufficient in order to do your diagrams. So that's the last 1-star question. Next video is the 2-star. Thanks for listening, guys. Bye.